My name's Zach Weinersmith. Have you heard of it? I'm more of an ex-KCD person myself. I have a couple announcements I'd like to make before we get into the show. Number one, I made an online promise, and promises on the internet are very serious. I made an online promise that if we sold all the tickets we put up for sale, I would say MIT greater than Caltech. And I should say my dad is a Caltech alum, so MIT greater than Caltech. But I just want to say, if anyone is watching the live stream and is a Caltech student or alum, I only did it for the money. I would never have done it if not for the cash. So anyway, I just want to say thank you to all of you for coming out tonight. When Christina told me our original venue was going to seat 500 people, I thought we'd be lucky to find 50 people. And I know this is Cambridge, but I thought surely there aren't that many dorks at this level of dork. But you have all surpassed my expectations. Yes. And I'm going to turn it over to Ben in a sec. He's your actual host for the evening. But I just wanted to say one more thing, because there's been a little bit of chatter online about this. I just want to be perfectly clear. We're not making fun of EvoPsych. We're certainly not making fun of evolution, because I got accused of that, so I don't even know what that means. So we're really just trying to celebrate that stupid thing you do where you come up with an idea you think is good, and then you stretch it, and then it explodes in your face tonight. And we want to keep it positive. If we were doing satire, we would have been way bigger dicks about it. Yeah, so thank you all for coming out, and I'm going to give it over to Ben Lille now.
Hello, everybody. I'm willing to bet that almost all of you have no idea who I am. Yes, thank you. That is how it should be. I'm Ben Lille. I run something called the Story Collider, where people tell true stories about science. And Zach asked me to host this thing, and like him, I had absolutely no idea what would happen. But unlike him, I didn't actually think we'd have a problem finding nerds at MIT. There was this amazing email chain back and forth where Zach's going, I don't think we'll sell out. And I'm like, it's MIT, you're going to sell out. And you all came, so thank you all so much for coming, despite the fact that you probably have no idea what's going to happen. We don't either, especially right now. But it's going to be amazing. I was really happy, as we're here at the first festival of bad ad hoc hypotheses, I was really happy that it rained today. Now, this is important, because as you all know, living in a rainy area is an evolutionarily adaptive strategy. Because if you are out on a date and it is raining, you have to get a little bit closer together. And that accelerates the relationship, and this is why people in Boston mate more often than people in LA. I have to say, I'm not entirely certain on the empirical data for that particular hypothesis. But I think it'll probably hold up, maybe. But this is part of what tonight is all going to be about. We talk a lot in science about the discoveries and the big things that happen in the lab, and people went and found amazing Higgs bosons and other things like that. I'm like, what's a science discovery? Higgs boson, okay. What we don't talk about is a lot about where these ideas come from. So like, we imagine, and you get from TV, that somebody is sitting at a transparent whiteboard and writing equations, and all of a sudden they understand everything about the universe and or how to solve the crime. And, you know, okay, science sometimes happens like that. But a lot of the time what happens is you are sitting in the pub talking to your friend. You're science people, you've all been doing this, and you're talking to your friend, and you say, you know, what if, and then you're both very drunk, and you go from there. And what's awesome about that is sometimes that works out. Sometimes that turns into an actual paper or a Nature paper or a Nobel Prize and fame, and those are not the ones that we're going to talk about tonight. What we're talking about here tonight are the ones that don't work out and are very silly and are very awesome. So you're going to hear 6 people who have bravely volunteered, despite never having seen this before. They have volunteered to come up here and give you their bad ad hoc hypothesis. And then because, and this is important, because the ultimate goal of science is to prove empirically that you are better than your peers. That's not a joke, that's true. And normally you do that with citation counts, but we don't have time tonight to go through that. We can't really collect them. So what we've done, in fact, is to put together an amazing celebrity panel of judges who are going to judge the presenters. And after they have judged them, we will crown a winner. And the winner, this is amazing, the winner receives this incredible prize. This is Darwin looking dubious. He says, I guess so. This is a one-of-a-kind prize. It was 3D printed. So unless somebody prints another one, it's one of a kind. But it is pretty incredible. Zach, you're going to tell us where this whole thing came from, because nobody knows.
Testing. Okay, I'm on. Wow. Well, I think in January I wrote this hypothesis that you can explain a lot of characteristics of infants if you assume that they're aerodynamic. And I don't want to give away too much because I'll be giving the full hypothesis shortly. But so I wrote this comic about baby aerodynamics. I'd love to know what the sign for baby aerodynamics is.
That is now my favorite thing that I have ever seen.
So I wrote this theory of baby drop kicking.
I think at this point, it's very much worth pointing out that Zach and his wife are expecting.
I hadn't thought about the implications of.
So you have no plans to conduct experimental tests?
I hesitate to answer that question.
I'm pretty sure the right answer is no.
Yeah, but I hesitate because I actually have an appendix in my theory today about academic bias against this sort of research.
But consider me the personification of academic bias against this kind of research.
Yeah. So this is I'm not even kidding about this. So I thought it would be nice to do a test of the baby aerodynamics, and so and as I don't know, are there a lot of biologists here tonight? So as you know, it's very hard to get permission from IOCOOK to do experiments on vertebrates. And so I haven't gone that route yet, but I got in touch with my local physics club, I won't say who, and I said, could we get access to a wind tunnel? I'm not even kidding about this. This actually happened. And what was funny is they said, sure, what do you need it for? And I said, well, I'd like to simulate a baby being catapulted through the air at high velocity. So the student I talked to, his name Nick, I won't say his last name. Nick said, yeah, I think we could get you access. I just need to talk to the professor. And the society was very excited. And then they talked to the professor. And the professor was confused. And what was funny, so I was hanging out on campus because my wife's a researcher there. And I happened to bump into Nick. And I was like, oh, hey, what's going on with the baby wind tunnel thing? And he said, I think if I just explain to him what's going on, he'll get it. And we got a no later that afternoon. So the point I'm trying to make is I think there's a lot of academic bias against infantipulting, is what I'm calling it, infantipulting, like.
That's a new kind of bias against science that I have not encountered before.
Yeah.
Probably because everyone agrees with it.
That's the definition of bias.
It is. Incidentally, you've all been to conferences, right? You know that at every conference, despite the fact that these are technical people, there is a failure. What I'm trying to say is this is on purpose. Actually, I'm curious, as a step out. He asked how many biologists are here. Can I get a round of applause? Who here is a scientist? Okay. And who here is not a scientist? Okay, it's about even, but the non-scientists were more vocal.
It's because they're happier.
Yes. I ran across a very strange incident of anti-science. We're all familiar with this guy and people who don't like him, anti-creation, but I said that wrong. Yeah. That one too. I was at the supermarket checking out, and for whatever reason, the young woman checking me out was very enthusiastic, and she's like, "How's your day?" And so I gave a real answer, and I was like, "It's all right, busy week," which you never do. But then she was like, "That's great, my week's been busy too." This is super weird. I'm a scientist. I never interact with people like that. So then she says, "What do you do?" And I never answer that question in a supermarket line either, but I told her, I have people tell stories about science. And she's like, "That's great. Are you a scientist?" And I said, "Yeah, I used to be a physicist." And she said, "Oh, that's interesting. I don't believe in physics."
And then she floated away.
Yeah. In the moment, all I could think to say was, and I actually said this out loud, "Oh, so you don't fall down." Which is kind of a dick thing to say. But then she's sort of handing me her groceries, and it got really awkward. And it's like, "Oh, that's interesting. What don't you believe?" And she said, I don't believe in all the forces and vectors." I mean, before I've encountered people who don't like relativity or don't like quantum mechanics for whatever reason, but that was a new one. Forces. No forces. They're bad. Okay, so running back to the point of this evening, which is that science is a competitive exercise and we judge ourselves against our peers. Hold on to that, that's the most important thing. So, let me now introduce for you our distinguished and wonderful panel of judges. Our first distinguished judge is Dany Adams. She is an associate professor at Tufts and also in the EBIX program here at MIT. She researches biophysical signaling during regeneration, which is amazing. Dany Adams. I should say, Dany also has a book out called Lab Math, which is all the math that lab scientists need to know but wished they didn't. Some of you need this book. It is amazing. All right. Thank you, Dany. Yes.
We'll just run.
Our second distinguished judge is Richard Wrangham. Richard is a professor of biological anthropology at Harvard. His major interests are primate behavior, the evolution of violence, human dietary evolution, and the conservation of chimpanzees and other apes. He's studied chimpanzees in Uganda since 1987 as director of the Kabali Chimpanzee Project. His most recent book is Catching Fire, How Cooking Made Us Human. Thank you so much. Richard. Our final judge is Robin Abrams. Robin writes the popular Misconduct social advice column for the Boston Globe, and she is also on the other page of paper. She is the author of the book Misconduct's Mind Over Manners, A Guide to Life in 21st Century America. She is also a researcher at the Harvard Business School and has a PhD from Boston University, and she is married to Mark Abrams, who runs the Ig Nobel Prizes, and she is involved with that. Please welcome Robin Abrams. It's been a long journey, but we are ready for our very first talk. Now, I said they would be judged. This one will not be judged because we've already made our judgment and we know what to make of it. Please welcome for the opening bad ad hoc hypothesis, Zach Weinersmith.
Babies are weird. They have a whole suite of qualities not possessed by adult humans, and we wondered why this should be. So there's a simple explanation we've come to, which is that early humans catapulted their infants over a nearby mountain to reach the next village over. And so it was adaptive for the babies to become as aerodynamic as possible to reach the most genetically distinct population. This simple theory has vast explanatory power, and I want to start you off with the physics of flying infants. So we started thinking about this, and our first model was airborne babies as tumbling objects. So in this case, it's somewhat explanatory because if you're a tumbling object, the best shape to be is a sphere. And we note that humans, with some exceptions, tend to become less spherical over their lives. But then we hit upon a second model. So this is an airfoil, the wing of an airplane, and this is the shape of an infant. Now, you will note that the large head of the baby, but the relatively tapered body of the baby, results in a low pressure zone above the baby and a high pressure zone below. So this creates some lift, but one problem that occurred to us is the baby has this large bottom, which is not aerodynamic. at all. And we thought, why should this be? Well, you'll note that if the baby did not have the large bottom, the center of mass is in the head. And so the lift is over here, but the center of mass is in the head. And so you're back to a tumbling object at that point. And in this configuration, the baby is very unstable. In fact, it's a particularly bad tumbling object because the axis is on the head. But if you add, as evolution has done, this bottom, it shifts the center of mass to the exact point at which it needs to be to catch the lift. And so that'll keep the baby self-balancing. Next we considered the fact that babies are largely hairless. Most babies have little to no body hair. And this is true even in populations that have long been in cold areas where it would have been useful. So we proposed that the lack of hair is in order to limit air drag while in transit. However, it's been noted, you'll see the baby has a little head hair, and we wondered why that should be. And I don't want to get too technical here, but we propose we propose that the baby's head acts like the dimples on a golf ball. And so by doing so, it limits the laminar flow, which results in this narrower wake here, so you get less air drag on the baby. And in addition, then, the rest of the baby is smooth because there are no major obstructions. And this is nice because it explains why we're attracted to people with smooth skin. In an evolutionary sense, we say, oh, this person will produce a more aerodynamic offspring for me. And it may even explain why we are attracted to people who are hairless below the head, but have lots of hair above. And it also explains why babies have these small noses, ears, anything that would get in the way of their two-dimensional cross-sectional wind-facing area. An additional thing, I don't know how many of you are parents, but you probably noticed that babies have this quality such that if you blow air on the baby's face, it will calm down, close its mouth, and relax. So we know from Galilean relativity that pushing air past the baby is the same as the baby being pushed past air. So we propose that this is an evolutionarily honed reflex the baby has to the flow of air past its face. It will remain calm and aerodynamic as it flies. And in addition, it'll keep its mouth closed, so it won't get an eddy current going. And also, it may be the case that by limiting the air intake, you also decrease the two-dimensional wind-facing area of the baby. And this also explains why babies like being tossed up and down. It explains why babies like it when you grab an arm and a leg and spin them around, because the baby, as it spins, is in an evolutionary sense thinking, this will allow me to mate subsequently with a more genetically distinct partner. So now we've gone over some morphology. I want to get a little more into behavior. Why is it that babies are so dumb? Now, so a baby cow is not much dumber than an adult cow. But a baby human is, with some exceptions, much dumber than an adult human. And so we wondered why this difference. So our proposal is that a smart baby would not get into a catapult. So, therefore, smart babies have tended to suffer a fitness cost from inbreeding with the local population, whereas dumb babies have gone very far. In addition, it's been noted that Neanderthals had not much larger, but larger craniums than Homo sapiens, and yet they remained regional and eventually died out while Homo sapiens flourished. It may be that their babies were too smart to get into the catapult. Finally, once the baby lands, it emits a high-pitched noise, which travels through the air, greater distance, higher fidelity. In addition, once humans find it, we note that babies are found to be cute by all human populations, regardless of blood relation or lineage. And so this is sort of a parasitic strategy by the baby to get its genetics into a genetically distinct population. I want to close with some historical evidence. So since this theory involves early humans, it's very hard to get fossil evidence. But we hypothesize that some primitive macrostructures, very large structures, may have been built to keep children amused and aerodynamic in flight. This is the Nazca Lines, Colossus of Rhodes, and of course the Sphinx. Now these structures are a bit too recent to have had a profound evolutionary effect, but we suppose that this is just culture reflecting the history of evolution, but that the impulse to build large, interesting pictures that could be seen from the sky is a genetic legacy from times when infantipulting was a bit more common. So you see great explanatory power of this theory. If you have any lingering doubts about it, we encourage you to look at your adult bodies and note that without exception, every single post-puberty characteristic you have would serve to create air drag while in flight. And in closing, I want to say thank you to Jacob and Joe from the Technically Speaking podcast, who had a very good knowledge of baby dynamics.
All right, thank you to Zach. Okay, so we're about ready to have our first speaker slash contestant slash, oh my God, what did they get themselves into? The judges. We'll be judging them on 4 criteria. First, they will be judging them on the force of the science. Basically, did they punch us in the face with a chart? Second, they will be judging them on the artistry. How well have they presented their bad ad hoc hypothesis? Third, they will be judged on their parsimony, or how closely did they shave with Occam's razor. That is the simplest theory that explains the most. And finally, on the strength of their defense, the judges will have a chance to ask them questions. How well did they withstand that assault? Which won't be all that assaulty, but still. Okay, with that, that is the FAPS system for judging, by the way. Yeah, I had to Google it too. All right. Are you ready to hear your first BA talk? Our first up is in fact an actual medical doctor. He received his undergraduate degree from MIT and his medical degree from Duke University. Since completing his residency in the Boston Combined Residency in Pediatrics, he has been working as a pediatric hospitalist in the greater Boston area. He's very active in the field of medical informatics. Please welcome Dr. Edward Chung.
I've been asked to speak to you tonight about my original research. It's called the geographic expression of evolutionary knack relative to underlying Lyme endemicity, or geek rule for short. My overseeing institution has asked not to be recognized at this event, and I've honored that request. So this is a talk about evolution, duh. As such, I want you all to keep one key concept in mind. That's selective pressure. Selective pressure is one of the key components that makes evolution tick. And what I'm going to show you in the next few minutes is how Lyme disease actually leads to evolution of people well suited to an advanced technological economy. Don't laugh. It's serious. So first, some background. You guys have all heard about Lyme disease. Many of you guys may have had it. We basically invented it right around here. Lyme, yeah. No, but seriously, Lyme, Connecticut's like 3 hours down Route 95. So if you really want to see the birthplace of Lyme disease, you can go do that. But it's a big deal around here. It's the most prevalent tick-borne illness in the US. There's about 20 to 40,000 cases per year. So think about a bad flu season. It's equivalent to that every year. The causative agent is this spirochete, this little green squiggly thing you see up there called Borrelia burgdorferi. And it's transmitted by Ixodes scapularis, which is a deer tick you guys all know and love. And sort of the pathognomonic sign for Lyme disease is that self-explanatory target lesion you see up there. That's when you see that rash in a doctor's office, you say Lyme disease. You're done. It's easy. What a lot of people don't know, though, is how bad Lyme can get if it's not treated in a reasonable time period. There's a lot of bad effects associated with end-stage Lyme, everything from meningoencephalitis to facial palsy to heart block to septic arthritis. Speaking from the standpoint of evolution, all these conditions reduce your reproductive fitness, and as a result, you want to avoid Lyme disease. This guy here, for example, he has Bell's palsy or facial palsy. The left side of his face is completely paralyzed. He can't wrinkle his forehead on his left side, he can't close his eye on his left side, and he can't really keep his mouth shut on his left side either, so he's going to be drooling. So I'm sure he's a nice guy, but he's not going on a date anytime soon. His genes aren't getting propagated anywhere. And when it comes to evolution, propagating your genes is what it's all about. So if you want to spread your genes, you want to avoid Lyme disease. How do you avoid Lyme? Well, the simple answer is you stay indoors, away from all those nasty ticks, right? So it follows that Lyme disease applies selective pressure to stay indoors. That's not the only way that Lyme applies selective pressure, though. As it turns out, the mainstay treatment for people of sexual maturity who have Lyme is the drug doxycycline. Doxy has the unfortunate side effect of causing extreme photosensitivity. So if, evolutionarily speaking, you're unfit/stupid enough to go outside and get Lyme, and then you're unfit/stupid enough to go outside while you're taking doxycycline for Lyme, you end up looking like this. Or like that. And again, no offense intended, but these folks aren't going on dates anytime soon. Their genes aren't getting spread. So again, the net effect of all this is a strong selective pressure from Lyme pushing people indoors. But here's where it gets interesting. In addition to staying away from Lyme, there's a lot of other benefits of staying indoors. You read more, you spend more time around computers, you learn more, you increase your knowledge. And in general, more knowledge leads to more success, higher status, higher wealth. So the end result of all this, selective pressure at work from Lyme, is that you get an adaptive phenotype. These are people who have adapted well to areas where Lyme is endemic. So these are people who are confined to indoor environments. They're pale, because they're not out in the sun. They're well educated, and they're good with technology. In short, they're geeks. And so it follows that geeks are exactly who we expect to see thriving in Lyme endemic areas. And what's more, people who spend more time indoors tend to mingle more with other indoor-centric people. So a couple pairings result, and the end effect of geeks mating with geeks is more geeks. Now that's a big-time evolutionary win. And why is it happening? Because of Lyme disease. And one more thing, this is just the icing on top of the cake here. Remember our friend doxycycline. This is the mainstay treatment for Lyme. Well, it turns out that doxy gives a little bump in evolutionary advantage to our geeks. The reason is that doxycycline hastens the metabolism of oral contraceptives. That's true. This leads, on average, to more offspring from geek pairings in Lyme endemic areas. Now, this advantage is especially important to geek populations, because remember, in general, the overall frequency of sexual encounters in this population is kind of low. So, you want some data? Here's some data. This map you see here is actually put out by the American Lyme Disease Foundation. It shows a distribution of the relative commonness of infected ticks in the lower 48. I'll point out the notable concentrations in the Northeast, especially around here, and in Northern California. So you ask yourself, what do these places have in common? They've got institutions of higher learning, just like where we are today. They have booming tech sectors. And what's fueling all this? It's our adaptive phenotype people. It's our geeks. This is exactly what you expect to see in Lyme endemic areas. So you're reading the paper about places like Seattle, Washington, Austin, Texas. They're concerned because Lyme disease rates are going up in their cities. They should not be concerned. They should be psyched. You want to... If you want a booming tech sector, you need geeks. If you want geeks, you need Lyme disease. That's Geek Rule. Thank you very much.
All right, thank you, Dr. Chung. Thank you very much. We have time for a couple questions for Dr. Chung. Our judges are stunned. Richard has one.
A good kind of stunned, I hope. A good kind of stunned.
I thought the case for the connection between Lyme disease and geeks is very, very promising.
Oh, thank you, thank you.
I happened to look up the dictionary definition of geek before I came here. It worries me. It's either an unfashionable or socially inept person, or it's a carnival performer who performs wild or disgusting acts. So I can be persuaded that with your mechanism, geeks are getting together and are doing better than they otherwise would. But how are they doing compared to the population as a whole?
That's a very good question. I mean, clearly they're doing better. Clearly they're doing better. I mean, we've all heard the saying, the geek shall inherit the earth, right? You're here. And it's clear from just looking at that map back here. I mean, look where people are thriving, right? Northeast tech sectors, doing great. Silicon Valley, doing great. Now Wisconsin, Minnesota. See, the issue there actually is there's not enough geek concentration. The people are spread out too much. They can't get together for pairings. So it's happening. I mean, these are like the whitest states in the country, right? I mean, these people are spending lots of time indoors. It's going to happen. Lyme just needs more time. So.
Any other questions from the judges? All right, thank you again so much, Dr. Chung. All right, second, we have Stacy Farina. She's a fourth-year PhD candidate at Cornell University who studies the evolution and biomechanics of respiration in fishes. Please welcome to the stage, Stacy Farina.
Hi, everyone. Thank you. I'm really, really excited to be here. Thanks so much to the organizers and you guys and Lyme disease, apparently, for bringing us all together today. So I'm going to talk today about the evolution and adaptive significance of low intelligence among fishes. So my hypothesis is that fish are pretty stupid. But not only that, in keeping with the theme of tonight, that it's adaptive, that it's an evolutionarily beneficial. So I start here with a graph of log body weight to log brain weight of vertebrates in general, so the major lineages. So if you notice here in blue, the ray-finned fishes, which are bony fishes rather than cartilaginous fishes, are lower on the totem pole of brain size to the other vertebrates. So it seems as though they have smaller brains. And we know from previous research that brain size correlates pretty closely with cognitive abilities such as social learning and ecological innovation. And so there is a link between brain size and intelligence among bony fishes. And so you can see, again, the light blue ray-finned fishes, pretty low brain size compared to even things like cartilaginous fishes, which are sharks. So if you would think, just looking at this data, that maybe fish aren't that smart because they're pretty primitive. They haven't developed intelligence. However, if you look at sharks, they have pretty high intelligence, and so you can hypothesize that the ancestor to sharks, tetrapods, and ray-finned fishes actually was pretty smart, and the presence of low intelligence in fishes is actually representative of a new evolution and actually an adaptive trait. I was really interested in trying to figure out more about the personality of fishes and intelligence in fishes, and so what I did was I polled my Facebook friends. I relied on the sort of crowdsourcing strategy, and I asked them to describe either their cat or dog or their pet fish in one word. And so they sent me a one-word response, and one axis is whether or not the word was more associated with intelligence or stupidity, and the other axis was whether or not in general it was a positive or negative trait. I found is in general, the words that my friends used to describe their pet fish clustered with words that were sort of related to stupidity. So for fish, they used carefree, brainless, dull, hungry. Whereas with their mammalian pets, they used words like patient, affectionate, strategic, loving. And the other thing that I noticed about this data is that many of the words that people used to describe their pet fish had sort of a negative connotation. In general, people don't think that the lives of their pet fish are really that great, in addition to people thinking that their pet fish are rather stupid. And so that led me to think about the link between intelligence and having a good life. So maybe if you have a bad life, maybe it's not such a good thing to be aware of it. And so I have here an adaptive landscape of intelligence among vertebrates. And you can see if a fish is more intelligent and more aware of its miserable life, for example, they don't have internal fertilization, which can't be really fun. Really low survival rates of larval and juveniles, and just really boring lives, according to my other data. They suffer a fitness drop if they become too aware of their plights. So it seems that there is likely an adaptive peak in an area of really low intelligence relative to the lives of sharks, mammals, and birds, which may have a higher peak where intelligence is actually pretty beneficial to them. Conclusion, fish are stupid because their lives are terrible, and if they were aware of it, then they would die. So.
Amazing. Thank you so much. Do we have questions from the judges? Yes, Robin.
Yes. It's a matter of some environmental concern nowadays, the amount of runoff in the ecosystem and in the wastewater from people who take, there's such a high level of people taking prescription drugs. I'm thinking now particularly when you have people, human waste with the SSRIs and the multiple pharmaceutical drugs that people are on, particularly psychoactive drugs, particularly in high-density urban areas. If everybody's just peeing so much Prozac into the water, do you think that this might eventually release some of the pressure on fish to be stupid, and seeing as how they're swimming in our Prozac pee? Well, you see where I'm going.
I think that would be a reasonable hypothesis to make. I actually think you might see some fish that are actually able to handle their awareness of their plight arising. And you actually may see the inverse effect with mammals and birds actually becoming less intelligent, or maybe just lapsing into existential crisis less frequently. So.
Is there another question? Yes.
Hi, lovely talk. I'm a little concerned about sampling bias and whether you've considered whether Facebook users just like stupid fish.
That could very well be true. I will tell you that I asked probably hundreds of Facebook friends, and I got a very weak response. So I tried to have a good sampling, but I think that I got at least a random sampling of people. So.
All right, thank you so much, Stacy Farina. All right, our third presenter, I'm apparently going through puberty. Our third presenter is Jordan Smith. He is a second-year undergraduate in biological engineering and political science here at MIT. Please welcome to the stage, Jordan Smith.
Cool. All right. So, hello everyone. Thank you for coming out to see my evolutionary hypothesis about mitochondrial hybrids and why they may have existed, and also to explain why Neanderthals are currently not around today. So, first, let's start with this clever graphic here of the migration path of Homo sapiens. So, humans originated in Ethiopia, modern-day Ethiopia, around 250,000 years ago. Within about 150,000 years, humans are practically everywhere, right? Like in a geographic heartbeat, pretty much we had dominated almost every corner of the globe and almost every climate imaginable. In order, for instance, to make it to modern-day Cambridge, humans would have first had to cross the Saharan and Arabian deserts, to scale the Himalayas, then to cross Siberia, swim across the Bering Strait, and then survive Canada. all the way from modern-day Ethiopia. Now, clearly, something gave our ancestors, I hope, a really, really good reason to move hundreds of thousands of miles away from their native land, besides lions, and something gave them the energy to make it happen. And so with that, we will start by talking about your mother. No, like, not exactly your mother, but why you should be thankful to your mother that she gave you these little deals called mitochondria in every one of your cells. Mitochondria are important for every biological process because they constantly produce energy in the form of a molecule called ATP. Without ATP, muscles cannot contract, neurons cannot fire, no cell in the body can function. And so with that, it's pretty clear that biology is incredibly, incredibly dependent on these organelles, but it's also important to note that humans only get about half of what we can obtain. You see, mitochondria, much like DNA, are inherited and passed down from parent to child. But in the case of mitochondria, only the mother's mitochondria are preserved. The father's mitochondria are marked and destroyed upon conception in the embryo every time. And so, what does this mean besides, all of your energy being from the mom's side of the family? It actually means that there is some mechanism that selects out the father's mitochondria, and for as long as we've known, it's not very clear, if the exceptions to this mechanism are possible and for what purpose this mechanism may have served. However, this hypothesis takes that and says, okay, well, if it is indeed possible for this mechanism to exist, it could have been seen in Paleolithic humans instead of today. And if humans, say, were to have this mechanism altered, it could lead to the support of two mitochondrial strains, two different types of mitochondria from both parents, to be supported by each cell. This would mean a doubling of mitochondrial energy, cellular energy being produced, and would therefore lead to superhuman abilities that can be likened to super strength, endurance, and metabolism. So, yes, the graphics are all completely accurate. So, if Paleolithic humans were able to adopt mitochondria from two parents, they would be able to have these traits. They could travel massive distances, they could scale mountains, they could swim across seas, and they would be able to survive the cold of the last ice age, the coldest parts of the last ice age, using super body heat. If you were to put this together into the map that we had earlier, would explain why humans were able to make it so far across the globe. This could explain why the natives of South America were able to settle the highest peaks of the Andes. This could also explain why the Maori people of New Zealand were able to make it to that tiny little island. And this could also explain why the natives of North America were able to survive, given the ever-present threat of the dread Canadian moose. And so, with that, we'd be able to see that, okay, with increased energy needs, this would require, increased energy would require increased energy needs. These individuals would require about 4,000 calories of energy a day, which is about twice of what we do now, with exceptions, and would definitely be much more than these humans would be able to achieve or obtain compared to today's supersized metrics. And so with that, we would say that since they were obviously traveling always, trying constantly in search of food to just feed their stinking superpowers, it would be reasonable to explain, why this came about. So, right, recall that originally mitochondrial inheritance is from only one parent, not two. And the exception for this would actually be something that was recently supported by the University of Citations Needed. And right, and this biparental mitochondrial inheritance would be able to support that this exception to the traditional mechanism is possible when you have two parents coming together to make a hybrid offspring. That is to say, when two similar but non-identical species are able to produce a hybrid, this could, because of the genetic differences between the two, bypass the traditional mechanism and allow for biparental mitochondrial inheritance. And so, what animal would have bred with humans to be able to produce this kind of hybrid? I say animal, that's kind of general, but it's really a humanoid that we're going to look at, which is the Neanderthal, or Homo neanderthalensis, but no one really likes that scientific name. So here with Neanderthals, right, when humans interacted with native populations of Neanderthals, usually in, you'd say Europe, I'd suppose, they were able to produce offspring. We've put together all possible permutations of human Neanderthal interbreeding for your convenience. They would be able to produce viable offspring if male humans, male Homo sapiens, bred with female Neanderthals. This would be produce a hybrid species that would essentially be two non-identical but similar humanoid species coming together, making a hybrid, which could thus bypass the traditional mitochondrial inheritance patterns that we see today. And so with that, we can say, all right, well now we have the stellar, flawless, I'd say, explanation for why we have mitochondrial superhumans existing in ancient history, but we must explain why they're not around anymore. And to begin with that, we would say why Neanderthals are no longer around. And it's pretty clear once you have this definition, this theory under your belt, to explain why Neanderthals went out. You see, clearly, humans and ancient superhumans teamed up together to effectively oust the Neanderthal, outcompete them for food, and outcompete them in territorial disputes due to their increased ability in energy and especially combat. Now, when these individuals would compete for food and territory, it would be pretty clear that the Neanderthals eventually, over time, would be outcompeted and phased out evolutionarily. This would then lead to the complete deficit that the Earth would have of Neanderthal females to be able to produce these mitochondrial superhumans, which would eventually lead to their own extinction. These individuals also would be the first to starve in cases of famine and the first to succumb to the most malignant tumors if they ever generated cancer. That's actually a citation somewhere that I'm not going to list here. So with that, we can say that eventually, after all that time, after all that competition, there could only be one Homo sapiens that could fill the space, the niche that was filled by superhumans, humans, and Neanderthals. So finally, just to get some primary sources up in this, I'm not going to fill that last word in. We're going to have this rock art, this specific cave painting that was found in the Drakensberg Mountains in South Africa that's dated to be about 20,000 and 10,000 years old, where you have these individuals over here on the right side of the image who are trying their best to sort of fight these three individuals here who happen to be very strong, almost radiating with energy that you can clearly see. So perhaps ancient humans were able to categorize and document the existence of superhumans long before we did. But for the rest of us, we can just thank our mothers for giving us the energy to live today. Thank you.
Thank you. Do we have questions? Yes, Dany.
Hi. A very interesting hypothesis.
Interesting, that's good. That's a good word.
I'm wondering if you could address whether this can coexist profitably with infantipulting.
I'm glad you brought that up because when I was working with Zach about this proposal, I sort of wanted to bring the idea that superhumans would be able to infantipult much farther than normal humans. Maybe about twice as far. Like maybe the difference between a really good kicker and like an average kicker, the kind of distance you could achieve. So yeah, that's great you brought that up.
Robin?
Yes. Anthropologists and archaeologists are beginning to find that in addition to the cave art, that fabric arts and fiber arts were far more common in the Paleolithic period than we had previously assumed. Would you hypothesize that one of the earliest uses for fiber arts was thus the manufacture of leotards and capes?
That sounds pretty sound. I think I'll use my vast variety of sources to be able to justify that.
All right, thank you so much, Jordan Smith. All right, our fourth speaker up here is Corey McLean. She is one of the world's foremost field canine phlebotomists. She is also an associate scientist at Biogen IDEC. Please welcome Corey McLean.
Hi, I'm here tonight to talk to you about a topic that's actually really near and dear to my heart. I started off as a scientist looking at flavor preferences in primates, actually working under Richard, who I did not realize would be a judge here tonight. And then moved on actually to look at domestication in dogs, which is how I wound up taking blood from dogs all over the world. So this kind of merges those two interests, and I'm going to be talking to you about why all of the species on this particular slide, and a large number of other species that I haven't been able to find good pictures of, are actually supposed to taste like chicken. So why do so many things taste like chicken? It might just be that human beings are very bad at describing taste. We really tend to say, oh, that's sweet, that's salty, that's spicy. But actually, as anyone who's ever been to a wine tasting can tell you, human beings can be incredibly imaginative about adjectives they're applying to food. So maybe the question should be, why doesn't everything taste like pork or beef? So if we consider the evolution of the animal kingdom by flavor, and here I really need to thank Joe Stanton, Dr. Joe Stanton of the Harvard MCZ, who actually published this lovely phylogenetic tree in the Annals of Improbable Research, despite the fact that I'm going to disagree with his hypothesis. So Dr. Stanton's suggestion is that actually human beings aren't tasting chicken, they're tasting the default tetrapod flavor, the default flavor of anything that is a four-legged animal. Now I have a couple problems with this. One, Dr. Stanton's research was based mainly off of his own flavor experimentation. Sample size of 1 is not fabulous, and he may have been somewhat biased in his choices of which species to taste. Number 2, there's particular species that are invertebrates that I think Dr. Stanton was remiss to not include, particularly termites and beetle larvae, which are said to taste like chicken. Now, given that these things taste like chicken, it doesn't actually make a lot of sense, parsimoniously, for fish and shrimp to not taste like chicken. If this is a default trait, then why do fish taste like fish, or why do shrimp taste like shrimp, instead of just tasting like chicken. So what Dr. Stanton thinks is just the default flavoring, I actually think is convergent evolution. When something tastes like chicken, it's because it's actually been strongly selected upon to taste like chicken. So I'd like to call this phenomenon gustatory mimicry. This is actually a relatively common phenomenon in the animal kingdom. You have species like the milk snake, which imitate the coloring of the coral snake. The coral snake is a very poisonous snake, and so by imitating the coloring without imitating the poison, the milk snake is able to send the message to predators and other animals, leave me alone, I'm poisonous. In just the same way, when, for example, frogs wind up imitating the flavor of chickens, they're saying, farm me, I'm tasty and delicious. They don't necessarily have to be tasty and delicious, they don't have to be healthy, but because chicken is perceived as delicious and healthy, they can do just fine. Now, you might think, okay, why in the world would you want to be a chicken? This is an animal that human beings eat. But as it turns out, the gene is selfish. It doesn't care whether or not it gets eaten so long as it gets passed on beforehand. Human beings are the most successful charismatic megafauna on the planet, and we are tremendously good at passing on the genes of animals that we like. There are dogs on every continent, and there are chickens on every continent except for Antarctica. So what's good for the goose winds up being good for the gander. If you taste like chicken, you're encouraging human beings to farm you, and therefore getting them to do all of the work of spreading your genes. So why doesn't everything taste like chicken? Consider the specific species that are using this strategy. These are species which will either be marginalized by humans or which are considered pest species by humans. So things like kangaroos, which may lose territory to humans, things like guinea pigs and termites, which might be considered pest species. So these are things that are going to have large amounts of contact with human beings, which means that human beings will have a chance to taste them, and human beings will actually consider tasting them because they're not particularly sophisticated predators. Obviously, polar bears are not going to be something that human beings consider farming because they're predators, and so they're not going to wind up being chicken flavored. The other thing that is required for an animal to successfully employ this strategy is a strong selective pressure or bottleneck to ensure the uniformity of flavor. So deer don't taste like chicken, but this is in part because, as anyone who's ever driven in the country at night can tell you, deer don't really seem to suffer from a population bottleneck because of their contact with human beings. So why does flavor mimicry require a bottleneck? That's mainly because the more genetic variation you have, the more flavor variation you have. And a bottleneck is going to reduce that genetic variation, and so it's going to reduce the flavor variation. So if a human happens to encounter your species and perceive it as a food item, then they're much more likely to get the same taste more than once and really get behind this idea of, yes, we should farm this animal. So why not beef or pork? As it turns out, it's relatively costly to produce beef or pork. We wind up having large-scale farming efforts for cows in America, but in many places, cultural taboos have evolved probably because of the large cost of producing pork and beef. And so it's just not as successful of a strategy to imitate pork or beef flavor because there are a lot of places in the world where people just aren't going to perceive that as a tasty flavor. Now, the last thing I want to address, you may have noticed on my first slide. You may have noticed on my first slide that I included a picture of Hannibal Lecter. As it turns out, cannibals have frequently said that human beings taste like chicken. Now, why would human beings taste like chicken? Because basically human beings are trying to promote bonding in as many ways as they possibly can. And so they're co-opting the wonderful, happy feelings that you get when you eat something tasty for basically bonding you to any individual you come into oral contact with. So the next time you kiss your loved ones, next time you kiss your loved ones or eat a tasty chicken or guinea pig or alligator, be thankful for the mutualism that makes it happen.
Thank you for that.
Thank you.
Do we have questions from the judges?
It's really more of a vocabulary question. Would you say then that there is a taste like chicken niche?
I absolutely think that there's a taste like chicken niche. I think that you probably originally had a number of other niches, but because chickens are so portable and easily farmed, that niche wound up being the most successful one.
Richard?
You said that as a consequence of humans tasting like chicken, humans bond with each other.
Yes.
Chickens taste like chicken.
So is your question
Can you talk
why?
about the bonding with chickens?
So I actually think that chickens wind up using this in a particularly different way. So if you've ever interacted with chickens or seen chickens, they're really unpleasant animals. They tend to peck at each other and taste each other, which I actually think it might be possible that they're seeing which of them tastes chickeniest and looking for potential mates.
All right, thank you so much, Corin McLean.
Thank you.
All right, our fifth storyteller. We are coming near the end. Our fifth, I did that again. Our fifth speaker is Tomer Ullman. He's a PhD student at MIT's Department of Brain and Cognitive Science, working on computational models of high-level cognition. That does deserve a woo. Computational models of high-level cognition, particularly in learning and development. Please welcome Tomer Ullman.
Annoying, isn't it? And therein lies an evolutionary riddle. Why is infant distress vocalization so particularly pitched and enduring? Surely, in the savanna death grounds of our early ancestors, healthy survival instincts would have dictated ditching these predator beacons, or at least preferring their quieter siblings. Now, previous attempts to explain this phenomena have cast the infants and adults at competing ends, with the infants trying to blackmail the parents into more resources. This is true. This is known as begging theory. But begging theory is in itself begging the question. Our proposal, by contrast, suggests that extreme infant distress vocalization, or crying, could only have survived if it offered some sort of advantage to humans, adults, and infants at the group level. And our hypothesis, which I'll explain in a minute, relies on both more classic research, which shows that intense infant crying raises the autonomic stress flight or fight response, and also on more recent research showing that adult humans exposed to intense infant crying perform significantly better on violent motor tasks compared to those who listen to things like birdsong or nothing. The task was actually whack-a-mole. In light of this information, the hypothesis is clear. Our early ancestors harnessed the natural adrenaline boost provided by crying infants by naturally harnessing infants to themselves and carrying them into battle with them. Now, the exact details of this process are, of course, lost to time, but we believe that several groups hit upon this independently, leading to the traditional garb still found in many societies today. Now, I know what you're thinking. Once stated, this might seem intuitive and even obvious, but we thought that we tried to delve into it and bolster it with some math. This math represents a computational model of many hundreds of tribes engaging in periodic conflict with one another over some number of generations. Now, I don't want to get too much into the technical details, so let's not. The actual paper is available upon request. I do want to give you the intuition behind that math. What we did is we simulated many hundreds of tribes. Each tribe contains 20 members, which is an ecological number. Each member carries one, for simplicity, quiet or vocal infant. The tribes are then randomly assigned, and they pair off with one another, and they might engage in conflict. And when they engage in conflict, the tribe with the larger proportion of vocal infants is more likely to win, thereby removing the other tribe from the population and spreading their own vocal genes instead. However, following this conflict phase, there is a culling phase, where vocal infants might be deleted and replaced with quieter infants. This bit flip operation happens with a probability proportional to a theta parameter, which we term unbearableness. Now, I'd like to show you some videos from our simulations. What we have here, each block represents a large number of tribes in different unbearableness regimes, because so what you'll see here is a movie of several tribes. Each tribe has several members in different theta parameters. There's low unbearableness, high unbearableness, in the middle, somewhere in the middle. So as you move forward in time, the unbearableness is quite low right over there, where everything turns green. You can see that each tribe quickly harnesses as much vocal infants as it can, and the vocalness spreads throughout the population. However, if the unbearableness is a bit too high, vocal infants quickly become phased out of the population. There's an interesting regime there in the middle where we expect a stable population of vocal infants. So what's the actual ground truth? Well, we can estimate the unbearableness by relying on our current best estimates for the infanticide rate in Paleolithic time. Now, most sources put this figure at around 15 to 20%. And when we plot this out, we can see that our model predicts that, given this figure, we should expect a stable, vocal infant population of between 20 and 35%, which is exactly the proportion of colic infants in modern human society, colic being extreme infant crying. Yes. So, having presented the literally incredible evidence for our theory from both psychology, physiology, math, and fashion, I'd like to leave you with this final parting thought. The next time that you find yourself in some cramped space with an extremely vocal, distressed infant, and you feel like you just want to kill somebody, take comfort in the fact that one of your ancestors probably did just that.
All right, thank you, Tomer.
If I may, I'd just like to thank my co-authors and also Gabriel Ullman for providing important input and motivation to this project.
All right, questions from the judges. Robin.
Yes. If you'll excuse a non-theoretical but more applied question, I do work for Harvard Business School, and I'm particularly in the field of corporate competitive advantage. What would be the implications for this on a more strategic rollout of Take Our Daughters to Work Day?
Thank you for that question. That's what's so nice about these conferences. You get a dissemination of ideas. I think the implications are quite serious, and personally I worry more about people who can't bring their daughters to work, because this is obviously an unfair advantage for those who can and enjoy this kind of adrenaline boost, which no doubt will result in a boost in productivity. So I think that as we move forward and our society becomes more tolerant, we'll obviously be able to provide some crying rooms for people who don't have children, and they can go there and listen to infant distress and therefore become more motivated in their work.
Richard?
Do you have any children?
Yes, that's Gabriel Ullman right there. One so far.
All right, thank you so much, Tomer Ullman. All right, we are at our final speaker. He is Dr. Justin Werfel. He's a research scientist at Harvard's Wyss Institute for Biologically Inspired Engineering. He works on topics in complex and emergent systems with a focus on swarm robotics. He did his doctoral work here at MIT. Please welcome Dr. Justin Werfel.
Thank you. The fundamental new principle that I have identified is that all animals tend to evolve toward a characteristic optimal body size whose length scale is set by that of the landmass or the body of water where they live. So to put that less formally, an animal living on a large landmass will tend to evolve to be large. An animal living on a small landmass will experience an evolutionary pressure encouraging it to become small. Now that simple mechanism explains a very wide range of observations. To start with, it explains why back in the days of the supercontinent Pangaea, the land was dominated by enormous reptiles and huge insects and so on, whereas today with the continents in their present configuration, the largest reptiles and dragonflies are very much smaller, now that that single large landmass has separated into several much smaller ones. The same holds true for mammals. Ancient animals like woolly mammoths and giant ground sloths have given way to today's mere elephants and tree sloths, which are tiny and cuddly by comparison. The same principle accounts for the well-known island effect, or Foster's rule, which observes that animals confined to islands evolve to much smaller body sizes than the mainland forms. So for instance, some of the largest sauropods, when confined to islands, evolved into closely related forms, a fraction of the ancestral size. The same is true again of mammoths. Of course, this is an animal named for being very large. Well, in many cases, actually, several independently documented examples of islands from California up to the Arctic, mammoth populations confined to these islands evolved to much smaller sizes. This is true even of humans. You may remember a lot of media attention a few years ago around the discovery of what the press called the Hobbit, the discovery of a small, at that time newly discovered hominin species on Flores Island. And in all of these cases, and in many other examples that I don't have time to cover, these are examples of a population being confined to a small landmass and evolving a small body size as a direct result. The same mechanism explains why marine mammals tend to be larger than land ones, and why, of course, the largest animals ever to live on Earth, not just the largest now, but larger even than the greatest sauropods back in the heyday of Pangaea, those largest animals are marine animals. And this is unsurprising when we consider that the oceans account for more than twice as much of the Earth's surface as does the land. Now, this mechanism has important implications for modern human society. Over the last century or so, advances in transportation technology have allowed many cultures to become increasingly interconnected with other parts of the world. And the result of that is an increase in the effective length scale of the living environment for humans living in these cultures. The effects of that can be seen most clearly in Americans, Because, of course, it's the United States that's really leading the world in this trend of increasing connectivity. The United States is the world's leading importer and one of its largest exporters, with 4 to 6 times the commercial activity of other leading nations. And it's also the country in which personal long-distance travel, and in particular air travel, has become most commonplace. So here I'm showing just domestic route maps for American Airlines only over the last several decades, just to give a sense of this increasing connectivity. So at the same time as these trends of increasing travel and commerce, Americans' body size has increased accordingly. And this is not just an effect of the last few years. This goes back more than a century, really to the beginning of this transportation explosion. Now, in contrast to the well-known American case, residents of less developed nations, where commerce and travel remain restricted, they live in an environment whose length scale is unchanged, and so they maintain a body size that's more typical of historical humans. You can see that very clearly if you look at a measure as simple as the total length of the road network in different nations, and plot the logarithm of that against the adult mass. The overall trend here is very clear. And if you perform an analysis of variance on this data set, turns out a remarkable amount of this variation in adult body size can be explained just by this one very simple, really crude measure. So this effect will be critical to take into account in planning for a future that may include space travel and extraterrestrial colonization. As we move from an environment of one length scale to one orders of magnitude larger, it will be crucial to take into account the corresponding increases in human body size that will inevitably result.
Thank you. Questions from our judges?
I have more slides.
So you would, according to this, you would probably predict that the Jetsons hypothesis was not correct.
Sorry, for the benefit of the audience, could you remind us of the Jetsons hypothesis?
The Jetsons were just a very slim outer space family, and it was a hopeful idea. It was a nice
hopeful
thought.
future.
Yeah.
A utopia, really.
Yes, exactly. So you're saying no?
It seems entirely implausible.
Does this hypothesis have implications for the potentially infinite space you can explore in virtual worlds?
That's a very interesting question. So this gets actually to a really critical question, which I think is actually the most interesting direction that this work then opens up, which is the question of how is this information about the landmass size obtained by the individuals. It's generally not going to be by direct inspection, right? There are very few cases where an individual is going to have a range on the scale of its landmass or its body of water, in rare cases. So somehow it must be getting that information some other way, presumably through interactions with other organisms, either its own species or even other species. There's plenty of examples of interspecific communication in nature. So now that we have discovered this principle, it opens up this critical question of how is that information obtained, and can things, as you say, like exploration of virtual worlds, will that carry the cue of being in a larger space? Like, will that have this effect on its own? And I think I don't have the data on this, but I conjecture there will be a correlation between people who spend a lot of time in virtual worlds, even today, and larger body sizes.
All right, thank you. Dr. Justin Werfel. Okay, Zach, if I could get you back up here. That was our final speaker, and it's now come time for the judges to deliberate. Zach is going to add up their contributions, but something that I didn't tell you, a special part of this, is that there's a final judge in the room, and it is you. It was really exciting. What I have in my hand here is a decibel meter. So what we're going to do is go through the talks that you have heard, and you're going to applaud for the ones that you thought was the best talk. And the judges each get to vote for their top 3 in order, and the audience vote will count the same. So just applaud for the ones that you thought were fantastic. And I'm just going to remind you very briefly. We had Dr. Edward Chung on Lyme disease. Stacy Farina, we're not doing the applause yet, I'm just reminding you what they all are. Stacy Farina on Fish Are Stupid, Jordan Smith on Superhumans, Corin McLean on Tastes Like Chicken, Tomer Ullman on Why Crying Babies Are Adaptive, and Justin Werfel on the expansion of the human body size. So, if you would now applaud if you were particularly fond of Dr. Edward Chung and Lyme disease. '92. I don't know what the units are. Okay, decibels, fine. Applaud if you particularly liked Stacy Farina on Fish Are Stupid. 95.3. Applause for Jordan Smith on Superhumans. 94. And for Corin McLean on Tastes Like Chicken. 105. Tomer Ullman on Crying Babies. 108. And Justin Werfel on Human Body Size. 99. Okay, so in a moment we're going to finish the final tabulation. I see that we're getting encouragement to be adrenaline-filled here. Before we announce the winner, we would like to do a few thank yous to everyone who has made this possible. Would we please have a big round of applause for all of our fantastic judges and the work that they have done here tonight. Dany Adams, Richard Wrangham, and Robin Abrams. We'd also like to thank Christina Shu and Hadassah Head and Zach, who organized this thing. We're going to have them on stage in a second, but thank you to them. We'd also like to extend a very big thank you to David Sloan Wilson and his projects, EvoS Consortium and This View of Life magazine for helping to make this event possible. Thank you to them. Also, similar thank you to breadpig for also helping to make this. Also, thank you to the SMBC team, Amanda Rossi and Michael Johnson for organizational work, and to the logo designer, Andrea Surumi. And finally, no, not finally, thank you to Rebecca Rohay for the site design and JP Bonner for purchasing the domain at lightning speed. Also, thank you to Eric Badger for his on-site help up there with the camera. And finally, the final thank you here is to Andrew Bach for designing this wonderful thing. No, I'm sorry, Andrew Bach made it a reality, and Kyle Horseman designed it. Thank you to them both for this extraordinary thing. And with that, sorry? Oh. Okay, it's time for the all-important moment. I've been handed the envelope, which is actually an imaginary one that Zach put in my head. The winner of the very first Festival of Bad Ad Hoc Hypotheses is Tomer Ullman, please come up on stage. Congratulations, sir. If you'd like to make a short acceptance speech.
Would I like to make an acceptance speech? I guess so. I'll keep it very, very short. I can't wait to hear what my son has to say about this. Thank you.
Tomer, stay here. I'd like all of the other speakers to please come up on stage. If you all would please come up here. And if I could also get Christina and Hadassah. Is Christina here? All right, so, sorry. Thank you to all of our speakers. And a thank you to the organizers, Zach, Hadassah, and Christina, who is probably running in from the merch table. There she is. All right. Thank you all so much for coming. We'd like to remind you, as you're leaving, that there is merch out in the table, and Zach will be there signing books. You can get him to sign them. And a very, sorry. Yes. Huge thank you to the interpreters who are the star of the show here. I think I'll remember baby hunting for the rest of my life. All right, and that is it. Thank you all so much for coming.